Hey everyone, I'm James Wang, Director of Product Marketing at Cerebras. Today I'm joined by JP Fricker, who is the Chief System Architect and co-founder at Cerebras. We read in the news that Nvidia's Blackwell is delayed, and it has something to do with these intricate interposers that they need to stitch together GPUs and memory. And I thought I'd talk to JP since he designed our whole system architecture to walk us through what might have happened and how we do things differently. JP, so this interposer issue, are you surprised at all?
No, I'm not surprised. Actually, quite expecting it. It's a very tough problem to have those large processor on very large interposers. But maybe we should look at it maybe a little bit closer to understand how an interposer is made. So here we have the floor plan of a package of a GPU, and in this case, you can see there are two logic die that are at the core of the processors, surrounded by multiple memory die. This is a typical package for such large processors.
But previously there was only one GPU.
Correct.
Blackwell is the first to have multiple logic.
Correct. So previously, imagine you have those memory devices much closer to the main die, and the package was much smaller, almost half the size.
Oh, wow. Okay.
What is happening when you build this is that, in fact, you need to think about it in the third dimension or a cross-section view of it. So at the system level, you have printed circuit boards within your servers. On those printed circuit boards, you need to put some processors. And what people do, they place the various silicon die that are manufactured on wafers, they place them on packages, substrates. So here is one example of such substrate.
This is the interposer?
So when you have multiple die, the substrate becomes named interposer.
Uh-huh.
And mostly because you have something that's between a die and the printed circuit board. You start to have a substrate, and sometimes to create the connectivity between these die, you use an interposer, something that is in between. So sometimes they put a silicon interposer on a package and then on the printed circuit board. Sometimes it's directly stacked as it is shown here. So let's simplify it and just say this is a silicon interposer, and you have multiple die that you need to interconnect between each other. So connectivity between the HBM and the die.
Now, what is different with the Blackwell generation for this layer versus previously with H100?
This is different.
The middle?
You now need to interconnect these two logic die with a very high number of interconnections between them.
So previously only logic to memory, now both logic and logic.
Yeah, so you need a very high number of interconnections. And because you now need a larger substrate, and those substrates are quite expensive, people decided that, why don't we use silicon just for what is super high density? So instead of using the entire interposer as a piece of silicon, why don't we use these as silicon devices? Silicon devices are nice because you can, on them, instantiate wires that are very, very small.
Okay.
Now, the substrate now becomes a combination of an organic material between layers of fiberglass and stacked with various organic materials, and these bridges.
That's the silicon bit.
That's the silicon piece.
Okay, so we have two ingredients now. That sounds all fine. What would be the problem?
Well, you need to align these very, very carefully so that they can match with or align with the pins that are on the bottom of these die and on the bottom of these memories. So you can imagine that when you want to align these bridges, you need to either start by aligning these bridges on the substrate and then put the die on top. That's one technique. I believe that's not the technique that's used here. They might be doing it backwards, where you actually put the die somewhere and you assemble the bridges on top of the first die. Okay. But everything can move as you process this, right? Okay. So just in manufacturing it,
just placing it,
maintaining that in the right place, and making sure that as you assemble this together, nothing moves, is very tricky. And when it's maybe manageable within this dimension. As soon as you get bigger, first you have more pieces to put together, but you also need to have longer distances on which you need to maintain the same precision.
What kind of scale are we talking about that we have to align, like these components?
So typically the pitch here is 10 to 50 micron pitch for those interconnections. That's a typical scale for those. The HBM now are getting smaller and smaller and smaller at each generation.
Align precise.
And that becomes a nightmare of alignment.
Okay. I hear alignment is part of the issue. I also hear thermal expansion differences are part of the issue. What's going on there?
So when you have silicon, these components here are made of silicon. This is made of an organic material. Okay. These bridges are also made of silicon. This one is made of printed circuit board. They have a coefficient of thermal expansion in the order of 10 parts per million per degree C or degree Kelvin. Silicon in itself is a CTE that's in the order of 2.6 ppm per degree C or Kelvin. So you have a difference in thermal expansion. So when initially they made this package structure on a large piece of silicon interposer, the CT coefficient of thermal expansion of both the logic die, the memory die, and the silicon interposer were matched.
I see.
So
that's on H100.
On H100.
Okay.
Then you go with a more advanced technique where you use bridges. In that case, you mix a silicon interposer with another type of material. It's a little harder to mitigate those differences of thermal expansion, either when you assemble or even after assembly. Because even after assembly, this starts to expand and contract at different rates based on temperature. So sometimes it starts to bow, and it bows differently.
Oh, it's like curves.
It curves.
Oh my God, that doesn't sound
So
good
when you
for
start to
electronics.
curve this, you can imagine all the tiny contacts that were supposed to tie these two together, they start to break.
Wow.
So, and it's very hard to maintain that. A lot of testing goes in it, and it takes a long time to verify that it works well.
I see.
And maybe here they didn't do enough testing, or maybe they were surprised by some scalability techniques, especially in production. You can make prototypes maybe very easily, but then when you scale in volume, the manufacturing process has to be adjusted for volume manufacturing, and it becomes harder.
That seems to be the problem. At volume, these things starts to warp, break, and this technique of assembling multiple different ingredients, different nodes into a single package seems to be like a nightmare.
Yeah, so there are two aspects, right? There is the material difference that contributes to the problem, and there is a size.
Right.
Because it's bigger.
This is the first time it's gotten significantly bigger.
Correct.
Since it's logic to logic. Now, when you architected the Cerebras system, you considered all of this and ended up with a very different design decision. Can you walk us through that?
Yeah, so when we started the company, we thought that we would look at the problem holistically, and we realized quickly that we needed more logic and more memory close to logic, and so we wanted a die that was bigger and bigger. We also looked at this technique of reassembling chips. But very quickly we realized that the problem that we would incur with one or two would be far worse when we go even bigger.
I see. So even if you solved it for 2 chips, once you go to 4, 8...
You're very limited very quickly.
Right.
It becomes exponentially, it scales with the size that you want to build.
Right.
And we thought that it would probably not be achievable, even in the time of a couple of years, to optimize the process to achieve this.
That was around, 2017?
2016 we started the company, so I spent about half a year to look at various techniques, and then about a quarter to further study yield models to understand how we could yield this.
Okay.
And very quickly we realized that the combination of dimension, various materials, various partners for different components and very many steps in the process would probably not yield correctly.
Okay.
There were too many steps, too many parts, too many partners to combine together. So we decided to simplify it and see if there was another way to do it.
Okay, walk us through it.
So what we wanted was a large piece of silicon. Okay, a wafer is about 300 millimeter in diameter. So this diameter is standard wafer size. And on that wafer, usually people build a step and repeat pattern of reticles. Nvidia does the same. Everyone does pretty much the same.
Yeah.
But then what people do, they typically test one of those, one by one. And once they found out which one is good and which one is bad, they mark the bad one. Then they cut the wafer, they dice it, and then they only keep the good dies.
Yeah.
And the bad one, they just discard them.
Yeah.
And then they package this onto a substrate.
That's what becomes one of those.
Exactly.
Yeah.
And when you want more silicon, what Nvidia did, they said, well, I want two of those on one piece of substrate. We found out that, well, instead of cutting that, what if I could afford to have defects? No one can build a wafer with 0 defects. So imagine you have many defects everywhere. Everyone designs chip with defects, like SRAM can be designed such that you have a little bit of redundancy and you can cope with defects. But if your entire logic design is capable of dealing with defects, then you could actually yield an entire wafer. If you have the entire wafer at your disposal, why not, in one area of a reticle, actually create a core that has both logic and memory very close to each other?
This solves the memory bandwidth wall that has plagued
Correct.
the whole microprocessor industry for
Correct.
decades.
So these two pieces being so close to each other allows you to have very, very short wire, much shorter than what you have here, very small amount of capacitance, therefore very low energy requirements to communicate. And also you distribute the memory over a larger surface, which allows you to better serve the various cores within a given reticle or large piece of silicon. While here, a core that's in the middle here needs to traverse and go all the way to the edge to get some information and all the way back.
I see.
Right? So there is a very long latency to get access to the memory, while here you don't have that latency. You have both bandwidth and super low latency.
Yes. Effectively, every other architecture, the memory and the logic are separate. We've combined them into a single piece because we're able to manufacture it so large.
Correct. We also made this core quite small. The geometry of this allows us to place about thousands of those cores in each dimension, X and Y dimensions, of our wafer, which allows us to get 1 million cores.
Incredible.
If among that 1 million cores we have a few that don't work, it doesn't have a big impact.
Right.
If you have a few cores that are gone in a GPU, it's okay. But if you have hundreds of cores that are gone, and because the cores here are bigger than our core that might be relatively smaller, if you have failures, this core needs to cope with many failures that for us would just be one of the cores being defective. And we can make this core, if it is defective, we can abstract it, remove it from the array, logically remove it, and abstract it to the upper layer software, and software can see this entire wafer as being a perfect wafer.
That's great. Let's get back to this. So how does this architecture avoid some of the complexities and pitfalls with the packaging problems?
So first, connectivity. Because you have these small cores, you can now actually have many of them interconnected on one reticle very closely, but also across reticles. And the lithographic process that you can use to manufacture the wires across is the same process that's used for wires within the given die.
How
it's
does
the
that
same process.
compared to like the interposer?
So here you don't need a bridge, right? Here you needed a bridge to go from one die to the next. Here to go from this die to this one because they're not cut. I can use the exact same material.
It's a native connection.
It's a native connection. And it is built by optical exposure, as opposed to a physical placement of a part that requires realignment. Here, I don't need to realign.
I see. This is one piece, and that's like plugging in something into the wall.
Correct.
Okay.
Okay, now I got a huge amount of bandwidth between radicals, equivalent to the bandwidth that I have within one radical across the various P. That's one aspect. Another aspect is packaging it. It's much simpler. The number of parts that I need to use to package it is reduced. I don't have that many parts. I don't have that many assembly steps to put it back together. I only have one wafer, which we call a wafer scale engine, one wafer, one printed circuit board, and one cold plate. In this case, they need more, right? You need the substrate, you need to solder this substrate to a PCB, you need these various die to be soldered to the substrate, you need the silicon bridge interposers to actually create the connectivity. So a lot of partners and assembly processes involved.
I see. If you call this the small chip approach, it looks like as we progress with AI and it require more memory, more bandwidth, the small chip approach gets increasingly, almost exponentially more complicated. The recipe gets more complicated, the tolerances are more demanding, and we stay as a single uniform chip with the same tolerances.
Correct. So we alleviate all these challenges, completely alleviated.
That's interesting. You know, when I remember when the first wafer scale engine was announced in 2019, it was very elegant, but the advantages were still a little bit more abstract because on the GPU side, they hadn't run into these issues yet. They were still on a more simpler. They didn't have interposers and all that stuff yet.
Correct.
But now, 5 years later, it really looks like this approach is at buckling point, whereas all the advantages for wafer scale are more apparent.
So if this seemed difficult, and we have proof that it was difficult for Nvidia to get that done with 2. We actually made it happen
for 50?
Quite a few years ago, right? Up to 51 of those, right? It's like 50x this size, and we got it solved with a simpler approach, a more yielding approach. And at the package level, we have similar components, but fewer of them and less sensitive to manufacturing processes for alignment purposes and so on. So for example, our wafer scale engine still needs to be cooled between a cold plate and still be powered from a printed circuit board, same as a GPU would need. However, our wafer scale engine is very flat. It's a single piece of silicon that's made very, very flat, which can easily be mated with a cold plate that's also very flat. And you can use a uniform thermal interface material that allows thermal connectivity between the wafer and the cold plate. While on a GPU or any reconstructed processor like this, you have various die that might have different heights, but most importantly, they might have different power consumptions with different thermal expansion, which causes this to be at slightly different elevation. So you need a thermal interface material here that needs to have vertical compliance. Another problem is with the CTE that you have here on the organic material and the silicon that needs to be bonded on it, the entire structure expands and contracts at different rates than the actual cold plate. The cold plate here, if it is copper, has a CTE of about 17 parts per million per degree C.
Oh wow, so we have 17, we have 10, we have 2.6, we have all these materials contracting and expanding at different rates.
And the printed circuit board is mostly the same as copper with a CTE of 17 ppm per degree C. So they mitigate the CTE mismatch with solder joints, with an organic material that has an intermediate CTE, and then trying to mitigate all that with rigid connections, semi-rigid connections. both on the thermal and the electrical side. We don't have to do that. We use a thermal interface material that can actually slide. Basically, we knew from the get-go that we would have that problem.
I see.
Right? The substrate expanding at a different rate. So we made it capable of sliding. So that thermal interface material for us is a sliding one. Same for the electrical material. Here in the center of the wafer, you have a direct connection. But then on the edges, you might have a different thermal expansion of the PCB that causes these connections that are initially vertical with temperature to start to bend. We invented a connector that can actually cope with that deflection, that CTE expansion.
You invented a flexible connector, one that...
A connector that can actually allow the two pieces to expand at different rates while maintaining connectivity. In this case, they can't. And this is part of the problem, is if you have such hard bonded component and you heat up or cool the structure, it will bow, it will start to move. And sometimes it moves so much that it starts to crack. It cracks connections, or it cracks solder joints, it delaminates. And this might be part of the problem that they're having, where maybe some of the connections are maybe not made from the get-go, but also break over time in the system.
Yes.
And here, what we have is something that on both ends allows this wafer to float and be completely independent of these CTE mismatches.
I see. So it looks like 6 to 7 years ago, you considered what happens when AI reaches scale.
Yes.
The chip is designed at a dramatically larger scale, and I think finally now with ChatGPT and Llama and things, it all makes sense because it's at the right scale. It's gigabytes to gigabytes, and we're the only chip with a petabyte scale compute and petabyte scale memory bandwidth. Never been done
Correct.
before. And on the system architecture side, pretty much all the issues that the Blackwell architecture is running into were kind of anticipated and solved ahead of time, well ahead of time. And the benefits only now are becoming
Correct,
clear.
right. This is a little bit something that takes time for people to realize, right? When you are deep into your own world of traditional chip making and you face a problem and maybe you have an easy way out of that problem, you keep doing the same thing.
Every step is easy.
You just continue, but at the end, it becomes a very big challenge. And if you don't step out of that mode of looking so close and looking a little further, you miss it.
Yes.
And you then continue to propagate challenges when it could be more easily fixed.
Awesome. Great. This has been super helpful, JP. Thank you for the session. We hope this has been informative, and maybe we'll do one again sometime.
Thank you so much.
All
It's
right.
been a pleasure.
Okay.